Good evening, sir.
Good evening, sir.
Actually, Professor joined and he sent a message. He will back in 5 minutes because still many participants have not joined. So Professor will back within 5 minutes. Hello, sir. My voice is audible, sir.
Yes, sir, you are
Hello,
audible. You are audible, sir.
hello.
Yes,
Yes, sir, you are
Voice is
audible, sir.
yes, sir. Your voice audible, sir.
sir. Good evening, sir. Professor Soundar Kumara, sir. Sir, no, sir. No, sir. Not hearing.
I can't.
So wait for a few minutes. Professor left the meeting. Sir, Professor muted, sir. Hello.
Hello?
Sir. Professor just joined and left the meeting, and he sent the message. He will join immediately.
Okay, sir.
Professor.
Vikram, sir.
Sir.
Sir has joined.
And the Professor just now Professor sent the message regarding the voice. Earlier,
Okay.
wait for few minutes.
Okay,
Some
okay,
technical.
sir. Okay, sir.
Dear participants, please wait for a few minutes.
Can you hear me now?
Yes, sir. Yes, sir.
Yeah,
Yes, sir.
what I did was that there is some issue with the Google Meet. So I called my phone and I'm talking from the phone. But let me try one more time from the.
Okay. Sir, good evening, sir. I hope there is good morning to you, sir.
Hello.
Sir.
Yeah.
Yeah, thank you, sir. Dear participants, today is a great honor for us to have the session of Professor Soundar Kumara, sir. And he is a mechanical legend in the field of AIML. So, and I request Professor Sriharin, sir, give brief introduction of the professor.
Thank you, Vikram sir. It's my honor to read out the brief profile of our eminent distinguished resource person of today's session, Professor Soundar Kumara. Professor Soundar Kumara obtained his Bachelor of Mechanical Engineering degree from SVU College of Engineering, Tirupati, M.Tech from IIT Madras, and PhD in Industrial Engineering from Purdue University, USA. His research interests are in thinking, sensor, data science, graph analytics, and large-scale complex networks, and AI and ML with applications in manufacturing and healthcare. Professor Kumara has worked on projects funded by reputed agencies and several industries, totaling about $45 million over his career as principal investigator or co-principal investigator. 64 PhDs and 76 MS students graduated under his guidance. Professor Kumara has about 300 publications to his credit. He has about 13,400 Google citations, 46 H-index, and his Erdos number is 3. He is a fellow of Institute of Industrial and Systems Engineering, International Academy of Production Engineering, American Association for Advancement of Science, and American Association of Mechanical Engineers. Dr. Kumara is the recipient of several awards, including the David F. Baker Distinguished Research Award from the Institute of Industrial and Systems Engineering, Research Excellence Award from ASME Computers and Information Engineering Division, Premier Research Award from COE Graduate Faculty Teaching Award, COE Graduate Faculty Teaching Award, and the Faculty Scholar Medal from Penn State, the highest research honor from Penn State. He is designated as one of the 20 most influential academics in smart manufacturing by the Society of Manufacturing Engineering SME in June 2021. In 2022, Purdue School of Industrial Engineering designated him as Outstanding Industrial Engineer, which is an honor 155 of the 10,000 living Purdue IE alumni have received. Professor Soundar Kumara is the Alan E. and Alan M. Pierce Professor of Industrial and Manufacturing Engineering at Penn State. He has an affiliate appointment with School of Information Sciences and Technology. He He is also serving currently as the Director of the Center for the Applications of AI and ML to Industry at Penn State. Thank you, sir, for your kind acceptance and gracious presence on this occasion. Now it's my privilege to invite Professor Soundar Kumara to take the session forward. Thank you, sir. Sir, over to you, sir. Professor Soundar Kumar, sir.
Can you hear me now?
Yes, sir.
Hello?
Yes, sir.
Yeah. I'm connected to the phone, so there's something wrong with the regular transmission. Such a section was not needed. I'm mainly a researcher, so everything is secondary. I think in the remaining 1 hour 5 minutes, I'll try to give a little bit flavor because it's very difficult in 4 hours and a half to give a good understanding of both artificial intelligence and machine learning and also the application part. Maybe all of you, if you can mute your phones, it will be easier because there is a lot of echo that is coming back to me. I would request you to mute your phones. Okay, I can get off the video and then I can use my slides to figure out here how to share my screen.
Project, yes.
Yeah, present now.
Later, sir.
I'm not used to the Google Meet, mostly it is Zoom, so entire screen. Yeah. Can you see the screen now?
Yes, sir. It's visible.
Okay. The AI and ML in manufacturing, some
Yes, sir.
personal questions. And if you,
Yes, sir.
if you cannot see it, you can't see me. You should be able to hear. I have. Don't be frightened that I have so many slides. I can stop at any time when you get bored or when I feel I've done enough. Yeah, thank you so much for inviting me. And I've known Vikram, Professor Vikram Kumar for a while, so I could not take up his invitation to present here. And thank you very much. So,
Thank you.
the organization of my talk is along these lines, some broad developments, and then AI and ML in manufacturing, a personal journey, intuitive explanations of AI and ML methods, statistics and machine learning, and some examples. So when I get to the time, please text me. I have 5 minutes left or 10 minutes left, then I can wind down my presentation. So the evolution of artificial intelligence is if you look at the philosophical things, and something which you can read very clearly is from Russell and Turing. And in 1956, the AI term was coined at Dartmouth conference. And then 1957 to 1980, there were several systems that were developed, including general problem solver, Dendel, hearsay, maxima, and etc. And then early neural networks was between 1980 to 1990, and then AI fell out of grace around 95 around that time, and then there was a silent period. Still, people were working in this, and then the IQ and the robotic things were still going on. Speech recognition actually went further and further. The neural networks came into the forefront around 2000 to 2015. That is the deep learning part of, and then the symbiosis of neural and knowledge networks, and explainable artificial intelligence and ontological based knowledge networks. This is the next one. And as we are speaking, the OpenAI chat GPT is taking over many things, and it is not so open. It is going to be initially people said that it's going to be all free, but I don't think it's going to be the case. It is going to be the closed AI. And then according to Kurzweil, the conscious machine possibly is around the corner around 2025. So going to the next slide, if you look at AI, is a bigger set, and then you have machine learning, both encompasses both like knowledge systems are both into AI and machine learning, and then you have the neural networks and then deep learning. This is one kind of a classification of the knowledge in AI and machine learning. And if you look at some of the machine learning models that are built on extracted features, the features are from the data. You try to pick up certain patterns, and then these patterns are used to fit models. So in that particular context, the regression model or decision tree models, which are like the random forest or ensemble methods, etc. Ensemble not necessarily in the decision tree, but could be. And then you have mixture of both these things. So models built on extracted features is one component, and models built on raw data. For example, the neural networks in the initial multi-layer perceptrons, and then now in recent times convolution neural networks, and then very recently in the last 3 years attention networks. All these things come into play. So that is the notion of the machine learning models. And I'm taking this route of going through some foundations and then explaining, because I was listening to the talks in the last 2 sessions, and then I found that if I start doing something on attention or deep convolution neural networks, that particular thing could be lost for the majority of the people. But for some of the people, what I'm talking may be a little bit elementary, but I can build on to give you indications of how you can use in different applications. And anybody interested in learning more can always connect with me. And there are a lot of resources on the internet and courses that are available, which will do an excellent job in each one of these methodologies. So what are some of the practical applications of deep learning? You can see that the self-driving cars or robotics or virtual assistants, and then language translation. These are all everyday affair these days. And then the colorization, and then facial recognition, and the healthcare. These are all different applications. And then the notion of personalized shopping or even entertainment, and then all the chatbots. Whenever you go to a particular website, a chatbot comes up and say, "Oh, can I help you?" And then it is basically AI-driven program, and then object tagging. So that when you tag objects, and then you can connect them together, build a network, and then from this network you can build clusters, and then you can analyze those clusters also. So that is some broader context of where AI and machine learning is. And then I hope everybody is able to hear me.
Yes, sir.
Yes, sir.
Great. And then I'm not unclear, I hope. So, yeah. And the next one is, this is like my own foray into AI and machine learning. I was one of the first graduate students who worked on intelligent manufacturing at Purdue, and then my PhD thesis was the first report on intelligent manufacturing that came out of Purdue National Science Foundation Engineering Research Center on intelligent manufacturing. And I worked on toolware monitoring, which is trying to pick up signals from the machines and then try to predict the health of the tool and therefore the health of the product. This is the body of work I did between 1989 and 91 with Professor Yang. Used to be my colleague, and then he is currently at Purdue. And then we looked into real-time monitoring. And then if you really want to do real-time monitoring, we felt that signal representation is extremely critical. Therefore, we did almost as we did work in this with a lot of papers published between 90s and 2000, 2001 on real-time continuous monitoring, process characterization with some of my students like Sagar and then Satish, and sensor data fusion with how do you connect, if you have many sensors, how do you use all the information together, and then how do you actually improve the sensor network's life, because when you have multiple sensors, they are connected together. When you have these multiple sensors to be in the order of hundreds or thousands, then the traditional techniques won't work. Therefore, I went into studying large-scale networks. So I studied graph analytics. Today, that's called as graph analytics. The first few things which I call them as data-driven engineering or data-driven manufacturing. And then the large-scale networks, we did a body of work, and then we have a bunch of papers in physics reviews. There, our claim to fame is we built a label propagation-based community detection algorithm. If you go to Facebook or if you go to the even current social media, you can build large networks. So these networks of the order of a billion nodes, maybe 500 million to 600 million nodes. So you connect two people together, perhaps based upon common interest, or could be from a common place or a common education, etc. So analyzing this whole network of 500 million nodes is not possible in real time. Therefore, we built a label propagation-based algorithm to cluster these networks based upon simply the topology, the structure of the network. So this LPA is used. If anybody is working in graph analytics, they will know this is a part of all software, right from Java to Python to iGraph. If you say LPA-based clustering, that is in large network, that is then the other body of work which we continued right from the early 90s to subsequently is engine-based manufacturing. And this we used in DARPA projects. My collaborators have been lucky to have some famous or very, I wouldn't say just famous, but very insightful people. So I learned a lot from them. Professor Hathwani, one of the pioneers, who is one of the first people who thought of computing and manufacturing together. So and then Professor Inyang Ham, Professor Hathwani is from Hungary. Professor Ham was my colleague at Penn State. Professor Yoshikawa from Japan. Sierra Wall, everybody knows Professor Rao is a statistician, and Rekha Albert, who is a well-known graph theorist, and so many other people here. In recent times, I've been working closely with Ram Shriram from NIST and Sudarshan Rachuri from DOE. Yeah, like earlier, we were calling a lot of these things as data-driven manufacturing, and now they all fall into data analytics or AI and machine learning umbrella. So one of the papers which you possibly can read, which is from 1999, in which we talk about the manufacturing in the digital age, This is with my colleagues Anand Balakrishnan, who is at UT Austin, and then Shankar, who is at the Rutgers. And then recently, Professor Sanjay Sharma, VP of Digital Learning, MIT, he texted me saying he read this paper. This was the history of the future written in 1999, which is, it made me feel good that what I wrote is not a waste. What did we actually tell in this? We studied kind of, there are organizational trends that are going on, and then information trends. And then you have the organizational needs, and you also have you also IT capabilities, and then these things converge to design and operation. So you need IT support for design, and then IT support for operation. This can be with respect to collaborative design or concurrent engineering, the project's monitoring or design improvement. Support for operation, which can be planning or supply chain or reactive problem solving based upon what you are monitoring. So all these things, the vital techniques are going to be intelligent search, collaboration, negotiation between different agents which are there, diagnosis and prognosis and learning from what you have done. And then software agents can become very critical. And this particular insight is valid even today. So there are quite a few publications we have, starting from one of those in CAR panels, Intelligent Computing Methods for Manufacturing Systems, and then Cyber Physical Systems agent-based. And then recently, in 2022, we published on the stochastic parallel mission scheduling using reinforcement learning. So you can look at them to have insight from the applications view and also what kind of techniques that can be used. So these are some of the books, and then this book, AI in Manufacturing and Theory and Practice, I edited in 1990. And then after that, I lost interest in doing any books. So what is coming to the core of the problem? Some intuitive explanation on AI and machine learning methods. So that's what I want to undertake now. That is the next thing. So this is from Yasser Mustafa's discussion. And in fact, a lot of people, many of you would have known about Netflix, the online movie platform. They had $1 million prize for improving their rating system. You know, how do people rate and then find out? So the fundamental assumption in this particular work or any learning classifier is there is a pattern that exists. When you say a pattern can be observed when you get repeated occurrences of something. If you have one-off or something happens only once and then you say you're going to build a classifier based upon that, you can't do that. And then, and also another important thing is we cannot have a precise mathematical explanation relating the observable and the outcomes. Outcome key is also an observable. So the inputs into your system and then the output of the system, if you cannot actually come up with a precise mathematical relationship, that will be their learning classifiers are very useful. We have data on the problem at hand. These are some of the foundational assumptions for building any machine learning technique. So how did this movie rating solution work? You have different viewers, like you and me. When we watch a movie, maybe we like comedy, or maybe we like action, and then maybe we like a blockbuster. Maybe we like maybe you like Akanin Nageshwar, or maybe he's not. I am aging myself here. I'm dating myself. Maybe you like movies with NTR or Shogun Babu, and then the particular movie. So how do you say that? Let's say you like comedy, and then you like Nageshwar Rao, and then you like historical kind of a movie, and then you like big budget movies. Like, and then you have movies which can be characterized by all these attributes or variables. Then the probability of you rating a movie to be very high increases when the distance between your liking and what movie is going to give you reduces. So based upon this distance, minimum distance is you give a better rating. That is what the foundational idea is. So you learn from this distance, right? So you could build a classifier based upon that. So the viewer and movie, and then the learning is trying to learn the rating. That is the foundational thinking in learning. The other example is credit card approval. Everybody will talk about it. And then you have the data about applicants. And then you have data about many people, many applicants. And then you have approved credit for a lot of people in the past. And therefore, when a new person applies, you are going to find the distance between this person and what you have observed from the past as a pattern. And then if the distance is minimum, then possibly you will say, yes, we will approve the credit. Otherwise, we will say, no, we will not. So very simple in conceptualization. So if you want to formalize this, you have an input. All the variables related to the customer application. Output is binary here, good or bad customers. If you want more, good, bad, or maybe not good, maybe not bad, you can use all these notions and introduce fuzzy logic there, and then you have, instead of a binary classification, you may have 5 classes and all that stuff. But fundamentally, let's say you're dealing with binary classification. What you're trying to do is, there is a mapping function F, which maps X, your input, or the predictors, to the output or the outcome Y. Okay, this is the best formula you can have. Okay, so what is it when you say the best formula? What do you mean? The error between a classification, that is, when you have a new entry coming in, there's a probability of an error. Error means you may classify this person to be wrong. The error between that and the actual observable is minimum. So that function will give you the maximum accuracy or minimum error. So you have data now. You have the historical records, X1, Y1, X2, Y2. X1 can be a set. Okay, not necessarily only. That's what we saw here, right? X1, in fact, is a vector of elements, age, salary, etc. So our hypothesis is we are going to learn this function G, which is among a set of functions, which will map X to Y. Okay, so that is what this function is, what we are trying to learn. How do we learn that function? Yes, we have the hypothesis set, the set of functions which are eligible to be used. And then you're picking up this particular function G, which belongs to this hypothesis set H, right? So how you're picking it up? Remember, we said we want to minimize the error. We are trying to do that. So this is what you call as the learning model. So it has the set of functions from where you're trying to take a function and the learning algorithm. The learning algorithm can be it can be your regression, or it can be your logistic regression, or your nonlinear regression, or support vector machine, deep learning. Okay, so I think after you learn what you're trying to do, you're trying to pick a particular function, and then you have the example, and then you learn using an algorithm, and then you come up with a final hypothesis. Okay, this function is the greatest, is the best function. So, one second, something happened here. Yeah, I think I pressed the wrong button. Then I need to switch. So, preventively. Okay. Is the screen okay now?
Yes,
Hello?
sir. Sorry. Yes, sir. It's okay, sir.
Yes, sir. Yes, sir.
So did I put sleep? Not yet?
Yes, yes.
Maybe everybody is sleeping now.
No, no, no. It's clearly visible, sir. It's clearly visible.
You can hear me well. Okay.
Yes.
So the idea of a generalized learning here is you have this function, some w's and xi, and then x's are given to you, plus some bias you're trying to introduce into the model, and then there's a sign of this, whether it may be positive or on the negative. We're dealing with two classes. And then this is here W0, I'm introducing an artificial coordinate X0, that is an artificial input to take care of the bias. So this function is, I'm talking to the linearly separable case. These are all your positive cases, negative cases. Positive cases approve credit and negative cases do not approve credit in this credit example. So we are trying to build this function. There is an ideal function, but we're trying to get a function. Now the function is defined by your W's. So the learning is nothing but figuring out these W's. Whether it is any kind of method you're using, you're trying to find the weights you can associate with respect to your inputs, whether it is linear, non-linear, or whatever function. There are two kinds of functions in general we're talking about. So if you take this one, this particular line, I need a pointer. This particular function, this is a linear, linear discriminant function, which essentially is not very good because there are two negatives are also associated with the positive and then more positive associated with the negatives, but this seems to be very good. So if I do this, then I have learned it. How can I do this? I repeatedly show to imagine you have a box full of W's. Okay, so this is like, let's assume that you are going to do it without replacement. You pick a set of W's based upon the number of X's you have, like your predictors, and then start putting the various values for the W1, W2, W3, W0 to, let's say you had three features, and then you look at all the possible combinations from the infinite number of W's you have in this bucket. And the assumption is finally we will come up with the best line. So if you leave it completely to the exhaustive search of picking up this infinite number of W's and do this, you spend your lifetime or 2 or 3 lifetimes doing it. Instead, we want methods which will look at some set of W's, produce the output with known samples. That is what supervised learning is. Compare it with the actual outcome. And then if they're okay, yeah, maybe these W's are good. Next, try the next example. Maybe the next example will not work. Next applicant will not work. Then you go back and change your W's. So repeatedly in an iterative manner, you do this. Then you have all this error minimization functions. How
Sir?
effectively you can do it.
Sir?
Sorry? Yeah.
Sir, can you please explain what is W again?
The W's are weights. Okay, you will understand it in the next one. See, imagine you are building a function, linear function, right? So next one, this is good. Can you see this? Let's say you're building this linear function, W1 x1, W2 x2 equal to theta. X1 and x2 are the two features or two variables related. And then you're taking, and then let this theta be some value. Okay, so let's say theta is 0, for example. Okay, W1 x1 plus W2 x2 equal to 0, or let's say 2, doesn't matter now. Now you take some W value, you know X's, right? The age of the person and then how much salary you make. You take this W value, which is called the weight, and then compute the value. If it is equal to 0, then you may say, I will accept the credit. If not, I'm not going to accept. How would you do this? Using the current data. For example, let's say I pick up W1 and to be 1.0 and W to be 1.5. This is the simple linear equation we all know. So I will substitute this W1 and W2 and then find out whether this satisfies the equation. If you're looking for it, you need infinite iterations when you have number of features, x1, x2 to x infinity, they increase. Therefore, you put a threshold on this. The threshold will be maybe greater than or equal to theta some value. Now the W0, if you remember, I can move theta to the left side, that can become a W0. So what you're trying to do is trying to find these W's so that you satisfy this inequality. Okay. Greater than or equal to theta. Left-hand side is greater than or equal to right-hand side. So learning or finding these W's is what you call as learning. Learning here refers to finding the values of Wj so that we get accurate classification. Does it make sense? So if you look at the
Now, I say your points.
Yes, sir.
So there are, in learning, there are different things. I'm sure in the last two classes, people would have talked about this eloquently: supervised, unsupervised, and semi-supervised learning. And then you have reinforcement learning. And then some of the things one should really recognize is labeled and unlabeled data. I'm going to talk a little bit about linear regression, visualization, logistic regression to drive home some points. So, you know, supervise this. You go back to your credit example. Okay, when you go to credit example here, age, gender, annual salary, etc. These are all your x1, x2, x3, x4, x5, x6, etc. And then you have values. You had, let's say, you're running a bank, and then you had 10,000 customers in the past to whom you have tried evaluating their loan application. Some of them you accepted, some of them you rejected. Let's say I build another column here, accept, yes or no. So accept means 1, reject means 0. So maybe for the first one you say 1, second one 0, so on and so forth. So this is the label. So for the predictors, which are the x values, you are giving a label, that is labeled data. So when you say supervised learning, then your input is this, all this, the output is the label 1 or 0 which you are giving. You are trying to understand that relationship. Supervised because you are giving this data which is known to you, which has the label. Unsupervised is you don't know this label. Let's say you just have this one. Then the only thing we can do is we can group them. So how do you group them? How do you group two things together? Suppose you are given clothes, different clothes. Your shirt, pants, bunian, underwear, socks. Okay. How do you group them? Shirts in one, all pants in another group, all underwears in another group, all bunians in another group, and then all socks in another group, right? That is clustering. So there are no labels. Let's say there are no. You don't know what they are. You only know the shape. Shirt looks like something, and pant looks like something. Nobody told you this is shirt, this is pant. Then the label is given to you. This is true in healthcare. Healthcare, when you have a lot of data about the patients, you don't have a label. Or when you are doing machine monitoring or maintenance activity, when you have not seen these kinds of faults before, you don't have a label. When you have seen the faults, you know. that surface finish is not good, or the bearing is not working well. Suppose you don't know that, based upon the signals you try to group them. That is clustering, unsupervised learning. And the third thing is semi-supervised. Semi-supervised is part of the data you have the labels and part of the data you don't have labels. So there are techniques to do that. And then the reinforcement learning is by repeatedly doing something, you understand that you are coming close to the goal. Okay, let's say you're doing scheduling. Let's take, a lot of you know the mission maintenance scheduling problem. And let's say you're trying to minimize the downtime. You're not going to use any simulation kind of an algorithm. You're going to take all these parts that need to be put on the machine and develop a schedule, and then see your schedule is good or bad, maybe total time taken. Let's assume all these combinations are feasible. Then what you do is you look at the total time, and then this is not according to what you read. Then what you do? You do to the next step where you try to build another schedule and see what is the total time taken. If the total time taken is less, then you have a reward to this particular method, to the particular state. So you keep repeating this so that this reward helps you to reinforce a good schedule. Finally, you come up with no further improvement in the reward is possible. That is a reinforcement learning. So labeled and unlabeled data, as I talked to you, is some of them you have the Y given to you, in some the Y is not given to you. Y is output or a response. Then let us look into a couple of these methods. So what are you actually talking about? This is your linear regression model, right? Y is beta 0 plus beta 1x plus epsilon or the error. This is the ideal model. Okay. And then the beta 0 and beta 1 are called the parameters of the model. Okay. And the epsilon here is, or the E, the error is a random variable. This is the error term. And the error variable is randomly distributed. And then this is the N is 0 sigma square. That is a characterization of the normal distribution. So how does the error actually behave? Okay. When you do a scatter plot, okay, you look at X and Y, and then if you build an average line in this, suppose you look into this, this is how the values are. Suppose I so if you let's say this is your average line, then these errors are like equally spaced, which means the variance is same irrespective of the value of X. So this is what you call as the homostochastic modeling. Okay. So if you look into the same sequence of vectors are going to have the same variance. This is an extraordinarily important thing for you to consider. If this is going to change, right? So then this is called as the heterostochastic data. So whatever learning you're trying to do, one of the first things you need to understand, how does this data actually behave? The assumptions that these are important. Linearity between X and Y, that is linear. If not, you go to non-linear method. When you go to the non-linear method, which power actually helps you? Non-linear to the order of 2, quadratic, or your cubic, or order of 4, or order of 5. The function basically, f of x is like x1 to the power of 5 plus x2 to the power of 5, x1, x2 to the power of 5, like this, or x1 to the power of 5 multiplied by x2 to the power of 5, all those kind of feature combinations. Can you really come up with theoretically and tell you this feature set is the best? No, not possible. And then another assumption is the variance of this residual or the error is the same for any value of x. It's independent. Observations are independent of each other, and then there's normality. So normality of x or any fixed value of x, y is normally distributed.
Sir,
So
can you please
limit,
explain the normality?
yeah, normality is a function behaves in a, what do you call it, this f of x is essentially normally distributed. Normally distributed means the bell-shaped curve. Okay, the
Sigmoid curve.
bell-shaped curve, particular functionality, right? People talk in common sense bell-shaped curve, right? Which will be like this, like a bell.
And sir,
Okay.
homosexuality?
Yeah, yeah. This is homostochasticity. Is if I draw a line here, x and y are x is observed and the predictor, y is the outcome. Now I draw, let's say, income and age or something. Then I fit a line here. Okay, this is the line. That's an average line. How do you fit the line? You try to minimize this error. Okay, this particular error, there are some above and some below. So the variance here is the what do you call the actual value minus the observed value here. The actual value is this. The on the this one, if you look put a not fit a line. You have points in this. You observe the, let's say here in this point. Your point on your estimate is here, but actual observed is here. The square of the difference, you have to square it, because if you just add this to this, some of them are positive errors and some of them are negative errors, it will become 0. You need to square it. That square is the the error term. The variance in the error. Variance here is the square of the standard deviation. Okay.
The upper line
Then,
is
this line is just a limiting line. You know, I'm just telling you here the observed data varies from here to here. That's it. The upper line has no significance. I'm saying my data lies within these bounds. And then if I fit a line, looking into the structure, I can fit a line like this. Okay. So this line is predicting you something, and then actually observed is, let's say, the predicting here, but observed is here. There is a difference. That difference is called as the error. And then that square of the error is needed, because if I just take the actual minus observed, sometimes it is positive, sometimes it is negative. You add all the errors together to find the total error, then it will become 0. So what do you actually do? You take the square of the difference. If you compute the standard deviation for that, then that remains the same, irrespective of x. Okay, that is, your data behaves in a particular uniform, not uniform, because it's normally distributed. I can claim this. So that is the structure of homostochastic. If your data is not like that, you can't go simply fit a linear regression. Okay, perhaps you need nonlinear methods, and then when you go to the nonlinear method, you have nonlinear regression. That is also one possibility, but I can't guarantee. But deep learning can help you. Deep learning can take care of a lot of nonlinearity in the data. So here y hat is an estimate. Okay, so that is, what is an estimate? It is an expected value of y given an x. An estimate is an average value. So this is my function. Okay, so we all know, we have drawn this graphs right from childhood. So b0 is our intercept, and then b1 is the slope, and then y hat. This is your simple linear regression equation. So this is the heart of this whole thing. And then how do you find this b0 and b1? Then you have ordinary least squares methods. So if you look at the particular function, you look into minima and maxima, and then we know we have done maxima and minima differential calculus. how do you compute? You take the first differential and then the second differential and then look at the positivity and negativity. Then this will comes up. OLS is a fairly simple derivation. So this is all one can say about regression. This is important for you to know because any other thing in deep learning you do, this understanding helps you. Then let us take a case. Okay, like I'm trying to classify the height of people and then gender. Okay, height given in inches. So 63, 70, etc. If it is 63, 1, otherwise the label is 0. Some thresholding we are going to use here. 60, here it is essentially like anything above 67, greater than or equal to 67 is less than or equal to 67 is a 1, otherwise it's a 0. 0 is a male and 1 is a female. If I plot this, height versus this, it looks like this. Okay, great. I have the data. I know linear regression. That is y is b0 plus b1x. And then this is how your the plot will look like. These are all the observed data. If it is a linear regression, this is going to be log. Okay. So the assumption on linearity will not hold for such a classification, so it will not work. On the other hand, suppose I fit something like this. Okay. Then my classification is much better because I can say, okay, anything anything greater than this value, maybe the 0, all are women. Anything above this particular value, and then anything less than this can be these values can be one classification. So this is the heart of your logistic regression. My beta 0 plus b1x this will not work. I'm using beta 0 b1 because they're all estimates. So then what I do is I just want to look into proportionality odds. How do you actually compute it? I'll show you here in the next thing. There are two forms this. The log of pi by 1 minus pi, that is one expressing this equation. Pi is given by this. I'm able to do this because of the normality assumption. And let's say you have the raw data. Okay. If the length of the golf, a lot of you may know about golf, and then the length is of the putt is 3, you made it, and then the 5 also you made it, but it was 7, you missed it. There are a lot of observations. You made the putt or you missed the putt. For length, so number made, number missed. Okay. So this data is straightforward to understand, and then this is the frequency you are counting. If it is 3 feet, you made 84 times, and then you missed 17 times, and then what do you call it? If the length is 4 feet, then 88 times you made it, and 31 times you missed it, and so on and so forth. So using this number of made and number of missed, you can see the proportion, right? The probability of making is this is pi is number of not probability of making. Pi here is the number. Number of made is 84. The total trial, the probability. The total trials is 84, and you have missed 17. That's what I didn't see this. Number of made, number of missed is total trials, number of made, so probability of making it. And then odds is computed by pi, probability of making it. Not making is 1 minus pi, because sum of two probabilities must be 1. Log of this, log odds. So go back here. My regression equation log odds, my y now in the regression you have equal to beta 0 and beta 1x. From the past data, I'm going to estimate beta 0 and beta 1. So I took a linear regression and showed you I can make it into a logistic regression, and you know why we made it. because when you have the binary classification and you're trying to use this, you can do ordering, but it won't work very effectively. You can have the logistic regression to your rescue.
So what is made and missed?
I'm sorry?
So what is this made and missed?
Oh, what is made and missed? Here, you go here. You know the game of golf? Okay. There's a game called golf, or you can take any game. Let's say, you know how people play goalie, right? In Andhra Pradesh, goalies are very common, correct? Are you with me? Hello?
Yes, sir. Yes, sir.
Yeah, when you play a game, you're trying to hit another goalie with your whatever you call it, right? That marble. Right? With one marble, you hit the other marble, correct? So if your length is 3, you are able to hit it. If your length is 5, you are able to hit it. If your length between your marble and the opponent's marble is 7 feet, then you will miss it. So you observe this data, okay? Length 3, you play, and then all your friends play, or maybe a group of people, or just you. When 84 times plus 17 times, so 101, right? 101 times you do this. 84 times, when the distance between your marble and the opponent's marble is 3, you are able to hit. If not, you are going to miss it. Then what is the probability of making? Number made divided by the total. That is what your pi is. Odds of making at 3 feet is pi by 1 minus pi. That is 8.8317 divided by 17 divided by 845. Whichever. And then log odds is 1.5976. Here in regression, you are calling y. Now this is your y. Okay. So then you have a continuous function. So because of the continuous function, if this odds fall less than or equal to some value, they're all going to be female, or greater than and otherwise they're going to be male. There is a classification, it is a continuous function, and there is much more value. 2 classes. It will work for about 5 classes effectively. With difficulty, the 5 classes, 3 is easy, 4 and 5 are difficult. And if the number of classes you have are going to be larger, then logistic regression is not the best thing to use. In healthcare in general, what happens is whether you have the disease or not disease, something is benign or malignant. So in healthcare, if you take 100 papers, 80 of them will use logistic regression. So that is the notion of logistic regression. So,
sir, one small doubt, sir. So why we are finding that log, sir, odd, sir, odd function?
Yeah, because again, if you look into these probabilities, okay, here, they are going to be very discrete. Okay, so when you take the set of odds, okay, in general, what people can, the way you would look at characterizing, what are the odds of a horse winning a race, right? That's how you would actually describe. What are the odds of making like hitting the other marble when the distance is 3? So the odds ratio gives you a better way of representing common sense, number 1. Number 2, when you take the logarithm of this, it will be a continuous function in a discrete case. That's why you take the odds.
Okay, sir. This pi, the discrete is continuous to continuous way. Sir?
Right, yes.
Okay,
Yes.
sir. Thank you.
Otherwise, you get that curve I'm showing, that height and the female and male classification. Okay, again, you'll end up with the same problem like a regression if you just take the probability. Yeah. And then the question we need to ask is what should be the size of my X vector? Okay. I would say I shouldn't say size of the X vector. Size of the X vector will be how many observations you need. That's a different story. How many predictors should we need? Like X1, X2, X3, each one is a predictor. So do I need 100 of these different features? Let's say I want to classify faces. Then features can be your nose size, your eyebrow width and eyebrow length, then your forehead width and forehead length, and then lip, upper lip size, and your ear length. Each one is a feature, right? Go to the credit example: age, income, marital status, whether you paid your taxes. All this can be features. How many of these features you need to do in effective classification? That is another important question you need to ask. Okay. So D is the dimension. Okay. So whenever you build, whether any kind of these models, in deep learning, that is not a big issue at all. Whenever you, but still, picking up the right features is an extraordinarily important problem. You can't take simply whatever you have and throw it into the machine. And Python can do any of these things today. You don't need to worry about writing the code. So you can't simply say all the features. You collected 1,000 features for each sample. That is your D. That is, so, and then say, okay, I'm going to do accuracy. My accuracy is great. No. I want to minimize the number of features I'm going to use. And then I say, how is my accuracy of the model? Accuracy is for classification in this particular case. I'm dealing with and supervised case. So then what you basically do is you keep increasing the features or go from 11 to keep reducing the features and see here if you look into the accuracy, after 8 features, for example, 96 is accuracy, the improvement is marginal. Okay, you add 9th feature, 10th feature, 11th feature. So maybe 8 features are enough for me. This accuracy is defined by the problem you are facing. In healthcare, accuracy need to be 99 point some percent. When you're dealing with airplane manufacturing, you are dealing with 99.98 or 97. That is the kind of accuracy you're dealing with any kind of a machine learning model. You don't want to get into a plane where the design of rivet, the way your machine learning model gives is 96% because the rivet can break anytime in from the wing, and then the plane can be in danger. You don't want to get into that flight. So depending upon the context, the problem context, you figure out what is your accuracy. But given that accuracy, how many features will be needed? So essentially, you are looking at how many features will give us a good accuracy. That is another important consideration you have to have. So the assumptions behind the data, and the model, and then the nature of your outcome Y, and then the number of features. These are some of the things you have to be very careful whenever you are trying to pick up your machine learning model. That is a lot of work compared to actually running the model. Okay, running the model, when I started doing it, I need to write the code and then do everything. It was painful. Today, running the model is the child play. Okay, but picking up the right set of data, right set of features, and checking the assumptions, and then checking the right model, that is critical. So another important thing you need to be aware, and you need to be looking at, is the visualization. Why do you need visualization? Okay. So what does visualization of data give you? It gives you the structure of the data. Okay. So this is a famous Ernest Combe data set. It's called Armstrong quartet. There are different values of x and y. Let's say x is your predictor, y is your output. This is set 1, this is set 2, set 3, set 4. Okay. There are 4 different sets. And then let me do a simple things here. Okay. What I will do is 11 observations I picked up, and I'm computing n equal to 11. Just let me focus here. I find the mean, the average, the standard deviation. This is R squared, not simply R. So when you look into this, look at set 1, the values are same. Set 2, all these values are same. These are the descriptive statistics. Set 3, the values are same. Set 4, the values are same. I'm happy. I know regression. I go fit. I have this equation for set 1. This equation, y equal to 0.5 x plus 3.009, and then this one, set 1, set 2, set 3, set 4, and I'm happy because this gives me an accurate classification and accurate fit of the data. But if you look into the data actually, see this, the structure of the data is very different. This is nonlinear, this is very different, this is like this, but my line is doing like this here, my fitted line is like this, like this. So you're going to be off track by doing something like this. So you need to visualize the data. At least in 3 dimensions, you can visualize. When the dimensions become, the number of features become 4, you cannot visualize. So, what if the number of features are 100, there is no way to visualize, but understand that visualization is important. When you have many features, the visualization is based upon the relationship between the variables. You can build graphs to do it. So, I think we are getting to the time, Vikram.
5 minutes ఉన్నాను సార్ ఉన్నానండి అంటే లేట్గా స్టార్ట్ అయింది ఒక 10 minutes ఉన్నాను సార్ 5 minutes సార్ ఏమైనా అంటారేమో చూద్దాము
Hello. Hello.
Hello, sir.
Can you hear me?
Sir, visualization means we have to just comparing different types patterns of data.
I'm sorry, comparing
Different patterns of data.
Yeah, different pattern. So, but see, when you have 3 variables, you can do it, right? Suppose you had y and x1 and x2. You can do a 3-dimensional plot. But you had, let's say, 5 variables. How can you plot? You can't really see it very well. You need to these techniques, and can I have a visualization to understand some relationships? Okay. So I think in order for you to master the machine learning part, you need to also understand visualization. Yeah. Yeah. Is Vikram Kumara, are you there?
Yes, sir.
Time, when did I stop?
Now time is 7:30, sir.
So I should stop now, right?
Yeah, if you want to.
I'll just take 10 minutes and then.
Okay, sir.
10 minutes and then stop. And let me go to the this thing here. I need to change it. Soft presentation. So let me give you a very brief my way of introducing people to neural networks. I'll try to spend 10 minutes and then you possibly will have some. Let's say this is a logical AND function, right? you know, what do you mean by logical AND function? They are looking into two input variables, x1 and x2. This came from electrical engineering, right? You have an AND gate, OR gate, exclusive OR gate, and all that stuff. So x1 and x2, when x1 and x2 is 0, let's say there are two lines, and then the current is flowing through these two lines. If you have an AND gate, it combines these two. If current flows through one line, as and also flows through one line, which means 1 and 1. If it does not flow through, it is 0. So if current flows through both of them, then the output of the AND gate is 1. Okay. And then both input 1 and input 2, there is no current. How do you measure current? You have the what you call ohm meter, and then you measure, and output is 0. That is one pattern. 0 and 1, again the output is 0 in the AND gate. That is another pattern. And then 1 and 0, x1 and x2 is 0, another pattern. And then x1 is 1 and x2 is 1, current is flowing in both, and then 1. So I just defined something called activation, which is W1x1 plus W2x2 is greater than or equal to activation, then it is 1, otherwise it is 0. So let me graphically put this in. This is the visualization part. 0, 0 is here, 1, 0. So I can draw a line like this. This is the linear discrimination function. And then in a simplistic case, it is called as a threshold logic unit. Threshold is W1x1 plus W2x2 is greater than or equal to theta. That theta in this case is defined by the activation, which is 2. So I can draw a line like this, and then keep moving this line. In the limiting case, line will pass through like this 0, 0. It will go through this. When you do this, or just look into it, any line above this, any point above this line will produce a 1 according to my function. So that is one classification. Any point below the line will produce this 0, 0, 0. 0, 0, 0 is one class, 1 is another class. I'm able to accomplish the classification. So this is the basic idea of a threshold logic unit. What does it really mean? I take W1x1 plus W2x2. That value is on my x-axis. This is your theta value. I'm sorry, this is your y value. Let's say my theta is 2. I will output a 1. 2 or greater than 2, otherwise I'll output as 0. I have accomplished the line here. They're able to fit this line. And then it can be positive or negative, or it can be a sigmoidal function. Let's say look into this one. Suppose you have x1, x2 to xm, different into this threshold logic unit instead of 2. And then you have W0, W1, W2, Wn. Remember the weights I talked initially, and then now I'm talked about 2 weights. W0 multiplied by input here, W1 x1, W2 x2, Wm xm, all are summed up here. That is your activation. You pass it through the activation function. These are the activation functions. And then let's say I'm using a simple hard limiter like this, right? So let's say just 2 variables, W1 and W2. W1 x1 plus W2 x2, and then x3 is minus 1, and W3 is greater than or equal to theta. Theta, I told you, like theta is the activation. Suppose you are using a hard limiter like this. So suppose theta is 2, anything greater than or equal to 2 is 1, otherwise it is 0. If it is sigmoidal, then what you are trying to do, this is your value A, 1 by 1 plus e power minus a, that is y. Y is, if this value is greater than or equal to 0.5, y is going to be 1, otherwise it is 0. So you show, how do you learn these W's? You keep showing 1, 1, whether I produce with the W's I learned. I have randomly chosen whether they will give a 1, otherwise if they give a 1, I go to show the next pattern, whether they're able to show both 1 and 0. one, next one. I keep repeating till my W's are such that I'm able to do this classification of 1 and 0. So this particular thing is called as threshold logic union. Now in current days, the activation functions are of different forms, and then softmax, and there are a lot of other functions that have come up. Softmax is one of the most used ones. Take several of these threshold logic units, simple things, connect them. Here you are just taking the inputs. Just taking the inputs here, and then you have a hidden layer, and then you have a hidden layer, many of those inputs, and then how many, the question is how many hidden layers you have, etc. 3 in earlier cases enough to do some non-linear.
Hello, sir.
Yeah.
So in simple terms, what is the definition of weight?
In simple terms, what is it? Yeah. Weight is the long-term memory in simple terms. So weights is, let's say here W1, right? Okay. And then is W2. You are, in a simplistic manner, though it is logically not completely correct, you are giving some weight to x1. W1 is a real number between 0 to infinity. And then you have one number here. And then you have another number, W2, here. And then try to, and then another number for W3. You know x1, x2, and x2 and x3, which is -1 values. You know them. Either 1 or 0 in this current flowing or not flowing case. In the credit case, you know x1 is age 23, and then x2 salary $1,000, and x3 is only the bias introduction, so it is -1 always. Okay. Now you compute this. When you compute this, is it greater than or equal to some theta? In this, suppose you are using this as an activation function. Let's say theta is 2. If it is greater than or equal to theta, you output a y equal to 1, otherwise y equal to 0. So those values of W1, W2, W3 are called as weights. So in the neural networks terminology, our brain remembers things by the synaptic strength. What is a synapse? Synapse is 2 neurons get connected together. They are not mechanical, purely mechanical connections. They are electrochemical connections. So when they are connected together, there is a current that is flowing through, energy that is flowing through. That energy is the weight. The way we remember anything is through those weights. This is a poor man or poor woman's example of our brain's, how it stores in memory, W1, W2. That is the simplistic but still valid explanation of weights. So
it is between 0 and 1.
I'm sorry?
Weights are always between 0 and 1.
No, I'm sorry. I told the weights are in any real number minus infinity to plus infinity.
Okay.
Okay. And that is the reason why actually you try to threshold it like this, or threshold it like this. See, suppose you had these values W1, W2, W3, any value between minus infinity to plus infinity on a real line, the total value is going to be infinity, right? Some of these things. Anywhere between, I'm sorry, not infinity, anywhere between minus infinity to plus infinity. That doesn't help us. That's why we want to threshold it. This thresholding is a very constraint. Here, you are taking that the value in the like a real line, and then passing it through a sigmoidal function, and then creating this nonlinear. So you are kind of taking this larger value and funneling through. It is like a filter. Okay. That's why it's called as a thresholding function. So suppose you had many of them connected together, that is what your neural network is. Here, this is your input, this is your output, and the computations are done and then here. There are no computations here, and a computation is done here also, because you're taking all this, and weights are on these links, W1, the weight between these two, weight between this and this, weight between this and this. You are connecting several of these threshold logic units together. And last 5 minutes, I will finish this just to give you an idea. Let's say you are trying to classify parts. In a very simplistic case, you can have black and white picture. And then let's say we generate a pattern, just a two-dimensional cross-section of this, taking this one. If things are filled, I put a dark, if not white. So dark and white can be, dark is 1 and then white is 0. Each one of these locations can be 1 and 0. Okay, simple way of representing these patterns. So my inputs now, let's say 5 by 5, so I have 25 x1, x2, x3 to x25. And here I want to produce the same part at the end. And then these are for these two parts. So these are all your inputs. You are connecting them to with some weights, right? I'm sorry. These 25 elements are here. 1, 2, 3, 4 to 25. These are connected to all this. Let's say the hidden layer, there are another 25 of them. And then this is the output layer, another 25 of them. This fact is represented, and then some random weights you are picking up. W1 to W26, W1 to 27, W1 to 28, like this. And then you do the computation. Sum them, pass it through an activation function, the output, do the same thing, the weight outputs, and then sum them up, multiply and sum them up together, send it here. Here, our objective is to produce the same pattern we showed here to here. Now, it may not be exact. This is what we really want to produce, but this is what we actually produced by using these weights. You find the difference. And then instead of throwing away, then technically I can get all new weights and do the same thing again. That will be a waste of time. Instead, I find the error. If 3 pixels are different, I'm okay. What do I mean by distance? This is a Hamming distance. 1 and 0 locations are different. If that is the case, up to 3 I can tolerate, then I have learned this model. Then I'll show the second part, third part, fourth part. Group technology, a lot of people may know group technology, then classification can be done. This is a very simple example of neural network. Today, deep learning, you have different techniques, but the idea is still the same. And then you have different activation functions, but still the way they are doing it. If you have, instead of what do you call it, 25, you will have a billion nodes, because we have the computational power. Still, what you do in each one of these nodes is the same. Sum them up, pass them through a thresholding function, produce the output. Now, depending upon in this billion nodes you are presenting, you can learn the features. So this is the whole back propagation learning, and all these things come. And then what I taught today, I should be teaching in about like 3 or 4 classes, but I could not go to many applications. But this is one simple application. In vision, you can do the same thing for surface roughness, pictures, or cavities on additive manufacturing. All those things can be anything visually inspected. Welding, like welding quality is good or bad. All this can be done with a simple thing like this. Let me stop here. And
Sir?
yeah.
Hello, sir.
Yes, I'm here.
Sir, how we can calculate the value of weights?
Value of?
Weights.
How do you calculate it? You imagine this, sir. So let me close this. Stop sharing. So the Okay. How do you answer this question? Imagine you have a big bucket. Okay. In this big bucket, you have weight vans, W1, W2, W3, infinity, W infinity, infinite number of weights are there. Okay. Are you with me? These are. And then you pick, let's say you have two features, X1 and X2. W1 X1 plus W2 X2. Let's forget about y equal to y. Okay, your y is given by W1 X1 plus W2 X2. Then you can do. So when you pick randomly two values of W, put them in your equation and see whether it produces your one or a zero. Because these values are your W values and your X values on a real line, what you want to do is to threshold this. That threshold is greater than or equal to theta. How do you produce the theta, whether it is a hard limiter, like a hard threshold interaction, or sigmoidal on say 1 by 1 minus A, what I do. So now put some W's, try to see whether you produce the correct Y. If you correct Y, you are happy, you have learned those words. But with one pattern hidden in memory, you have many patterns. In our AND there are 4 patterns. You keep repeating these patterns and come up with this W1 and W2, unique values of W1 and W2, which will classify all these patterns correctly. What I mean by correct class? If you give a 0, 0, it is class 2. If you give 1, 0, class 2. 0, 1, it is class 2. If you give 1, 1, it is class 2. So if you are able to do that correctly, then you have learned you have calculated. Extend this argument and extend to all real values. When you produce a y, y is a real value. When you find the difference between the y generated by w, you actually observe. This is a supervised learning. And find the error between them. If it is acceptable, you say my w's are good. If the error is not acceptable, your w's are not good. So keep repeating like in the two variables. That's how you learn your learning. That is what the essence of learning is. Okay?
Yes, sir. Sir, why Python is used in AI, not other programming language?
Say that again.
Sir, why Python programming is used in AI?
You can use R if you want. You can use Python. If you want to write, you can write in C++. I wrote all my code when I was like you in C++.
Okay.
Python is more popular, it's very easy to use. And these days you don't even need to learn programming. You use GPT. It actually gives you a code, but to run the code you need to know the basics of programming. So I think Python has been easy to use and it will optimize on performance. Even R is easy to use. When I teach my graduate courses in learning, I used to when initially used to list there is a list processing language there, and then I was using C++, then I used R, and then now I'm using Python. So it is a matter of popularity. And Python has modules for everything. Yeah. Let me stop here, Vikram. There are no other questions.
Thank you, sir.
Thank you.
Any questions from audience?
Okay. I think when there are no questions,
Thank you so much, Professor, Dr. Venkatesh, on behalf of faculty team from IIT Bangalore. Thank you so much, sir, for your time and valuable information. We are enlightened with your presence and presentation.
Yeah, thank you. Bye. Thank you.
Thank you so much, sir.
Should we start the next session with introduction with yeah.
So let me now, Venkatesh sir, let me now conclude the summary of Professor Soundar Kumara sessions, and quickly I am going to rewind the topics he touched upon and the interest he has created towards this journey of AI and ML. So initially, when Professor Kumara was talking about the evolution of AI, and he has laid out here his personal journey also, and he mentioned some of the areas he worked initially: tool bearing monitoring, sensor data fusion, and large scale networks. That was the point he mentioned. Graph analytics, and some broad developments also he laid out in the initial phase of his session. And one of the emphasis point during this session was generalized learning. There he mentioned very much about the weights and how to now reduce the error, and thereby we can now get proper weights in the process of learning. That was the point he was highlighting. And there are five or six points he was mentioning about the learning. Supervised learning, he took that. See there, there is nothing but labeled data where you can get zeros and ones, and unsupervised learning. He was mentioning about the grouping concept, and by the help of some live examples of taking clocks and something like that, various kinds of clocks, and how do we group it? That is one of the important concern here. And he was mentioning about one example of healthcare fit into the unsupervised learning, and these are the kinds of the phases he put forward. And he mentioned about reinforcement learning. He took an example of maintenance in that total time calculations for the maintenance problem, and how to now learn there, and further no further maintenance problems comes. So how to make the weights so optimum so that we can now minimize the problem. That was the point he was mentioning. And he mentioned about the two important models in the linear, maybe two important models: homostochastic model and heterostochastic model, stochastic model. Where in the homostochastic model, he was mentioning about there was no variation in the output as the input changes, and the case of heterostochastic model, he was mentioning about the variation of y with respect to x. And these are all the main points he was mentioning. So with this, I really thank Professor Soundar Kumara. He has spent a lot of time, though, in spite of his busy schedule in the overseas. So very happy to hear you, sir, from you. We were eagerly waiting about this particular session. So you made the session very fruitful, sir. Thank you.